Today I'll finish up talking about flashlights and go on to talk about household magnets. And I feel like I've got four things I want to look at and make sure I've sort of passed along to you. Well, the basic idea with flashlights is these are all electric circuits. They have a source of electric power, which is in this case the battery, and they have a consumer of electric power, which is a light bulb or potentially a light-emitting diode, which is a little more sophisticated and we'll deal with later. Just to complete the story of this sort of exploded flashlight here as it stands, when I close the switch, and first of all, you need to close the switch, which is jargon for creating a complete circuit, because, I've harped on this already, the purpose of the whole arrangement is to deliver power from the battery to the light bulb. The light bulb is not collecting charge, it's just collecting power. And so the power flows through the circuit, carried along by the electric charges, the current, that's the moving flow of electric charges. But the electric charges go back to get more power. Their purpose in life is not to arrive at your house. They're there to deliver power. Okay, how would you calculate how much power is involved? Did I lose something here? Yeah, okay, I'm still here. How much power is involved? The power that's provided by the battery, and so there are two equations up there in yellow. The power that's provided by the battery is simply the product of the voltage rise in the battery times the current flowing through the battery. Why is that? The voltage rise measures how much energy per charge. Energy per charge. It's for each coulomb that goes by, a coulomb of charge that goes by. If you've got a 12-volt battery, that coulomb picks up 12 joules. So it's getting a certain amount of energy along with it. If you then look at how many coulombs are flowing through the circuit every second, that's the current in the circuit. So if you take the product of the energy per coulomb, that is voltage, that's picked up, times the coulombs per second, that's how much current flows through, you get the energy per second, which is power. And long and short of it is the product of those two quantities. The voltage rise in the battery and the current in the circuit gives you the power that's being picked up in the battery. And there's a corresponding power relationship for the light bulb, the consumer of power. It's experiencing not a voltage rise, but a voltage drop. That is, the current that enters it arrives at high voltage, high energy per charge, and leaves at low energy per charge. So it's dropped off energy. And how much energy does it drop off every second? You multiply the amount of energy per charge that's dropped off times the amount of charge per second. Energy per second, that's power. So the power dropped off is the voltage drop in the light bulb times the current flowing through it. Will I ever ask you to calculate this? Only a little bit, I guess, in the problem set. But this is worth knowing just in general for future reference, that the details of the circuits that run around in your house they're more sophisticated often than this battery. There are some complications that we'll come to associated with the power that arrives from the electric company. But still, if you have, for example, a toaster that you plug into the electric outlet, the amount of power that's arriving at that toaster is going to be the voltage difference between the arrival voltage and the departure voltage. The voltage, the current will show up at the toaster at high voltage and leave at low voltage. There's going to be a difference in voltage. So the amount of power that's dropped off in your toaster is that voltage difference times the current that's flowing through. How many amperes? And if it's, say, 120 volts is the difference in voltage, the voltage drop in your toaster, and there are 4 amperes flowing, then it's 120 volts times 4 amperes. That's 120 joules per coulomb times 4 coulombs per second, which gives you 480 joules per second, 480 watts. That's what your toaster's consuming. If you plug 2 toasters in at once, same voltage drop, but now you've got 2 toasters going. They're going to be taking not 4 amps, but 8 amps. That's twice as much current, and in this collection of toasters, you're going to get 120 volt voltage drop times 8 amperes 8 coulombs per second. That's going to be twice the power, 960 watts. And so it goes. Is that okay? Just for reference in your house, most electric outlets deliver essentially 120 volt voltage drop. There's a nuance here because it's what's known as alternating current that we'll have to come to. But it's essentially 120 volt voltage drop. And the outlet is capable of delivering, depending on the outlet, 15 amperes or 20 amperes. If you don't want to go beyond these maxima in protection circuits, protection of devices will open the circuit for you spontaneously. Fuses and circuit breakers will open because you're taking too much current through the circuit. But if you stay within the safe boundaries, that means that if you've got a maximum, let's say, of 15 amperes available from an electric outlet at 120 volts, that's 1,800 watts. That's all you can get out of that outlet. That's if you get the entire 120 volt voltage drop and all the current the outlet's capable of supplying, which is 15 amperes. At 120 volts, that's 120 joules per coulomb times 15 coulombs per second, that's the current, is 1,800 watts. You can't go beyond that. Something will go bad. Is that okay? Just basic observations there. All right, so that's one thing I want to do is make sure that we looked at the power in the circuit and how you calculate power. Next thing I want to just jump to, and I'm not going to do it by way of with the view graphs. Short circuits. It's a term you've heard your whole life. It's used in random ways often. It's a short circuit, to my mind, a physicist's version of a short circuit is literally a shortened circuit. That is, instead of having the circuit involve all the wires and the light bulb that you had in mind, you introduce some way in which the current can skip parts of the circuit, take a shortcut. Okay? The shortcut that I have in mind in this circuit will be around the light bulb, and that's the one that's most dangerous. At the present, I've arranged it so this circuit actually has already secretly in it a thin piece of wire that wasn't there Wednesday. So the circuit, it's still basically a battery, a light bulb, and some wires. But one of the wires is set aside because we're going to make it hot. Okay, it's going to get too hot for comfort. So the current's is leaving the light bulb from the positive terminal, which is the high voltage end. It's being pushed through the wires by way of a slight voltage drop in the wires. They develop a little bit of an electric field that helps the current go through them and keep moving. The current gets to the light bulb. Now it needs a huge push to go through the light bulb because the light bulb is a poor conductor of electricity. Its filament is a poor conductor of electricity. It needs a big push. Current needs a big push to keep going through that light bulb filament. And so it needs a large voltage drop across it to create enough of electric field to keep the current moving. So most of the voltage rise that was provided by the battery goes into a voltage drop in the light bulb. And then the current continues on through this funny wire and then back to the low voltage side of the battery. It's pushed along by a small voltage drop in them, which is necessary to keep the charge moving, and it gets back to the battery pumps it again, and it goes around the circuit again, over and over again. So far it's the same old circuit. Any questions about the circuit? Excuse me? Could I zoom in? Thank you. Sure. I can. Zoom. Okay? Woo, woo. And so there's this funny set-aside wire. And right now everything's okay, no problems. But what happens if we introduce a shortcut for the current? We allow the current to come out of the battery, go through a little bit of wire, and not go through the light bulb. Find a bypass. People are always trying to build bypasses. Okay, so we'll build a bypass for the light bulb. So I'm going to go from here on this side of the switch with a wire. I'm going to just go right around the light bulb and plug it right into this end. Oops, I overshot here. Plug it into that part of the wire. Wow, that's interesting. The light bulb went out. Look, if I undo the shortcut, no problem. The light bulb went out. What happened? Well, I've now provided a path that the current can take that doesn't include the light bulb. I mean, some of it can go through the light bulb, a little bit of it's going through the light bulb, but the vast majority of it has an easier route. Remember, the light bulb's got it has a large electrical resistance, which I will come back to in a few minutes. Means that you have to push hard to get current to go through it. It needs a large voltage drop to drive the current through it at any decent level. It's skipping, that's a difficult path for the current to go through. The current would much rather go through a wire, and it does. And so most of the current, at this junction point here, the current has got a choice. Go left, go right. Oh, well, most of it goes right. And it's rushing through that wire, and it continues on to the battery. And you might notice something going on with that wire I have over there. It's harder to see on the zoom in because you don't get the color, but it's red hot. Okay? What happened? We edited out the designated consumer of electric power. The light bulb's job was to consume the power that the battery provided. Actually, I'm going to stop this before we start a fire. It's starting to, well, it's smelling like burned stuff because I burned stuff. All right, but the current was supposed to pick up energy in the battery, drop off energy in the light bulb, which safely consumes the energy and does something interesting, makes light. And it also gets hot, but it's not. It's designed not to start fires easily. By bypassing the light bulb, we picked up energy in the battery, and the current picked up energy in the battery, and there was really no place for the current to drop off that energy. And instead, it drops it off in the wiring. And actually, because it's an ongoing process, instead of talking about energy, I should talk about power, energy per unit of time. So a fair amount of power was being picked up in the battery, maybe 1,000 watts actually at this point. 1,000 watts of electric power being picked up by the battery, from the battery, and then dropped off in the wires, because it's got to go somewhere. Energy is conserved. It went into that wire. That wire was, I picked that one out because that wire is not as good an electrical conductor as the other wires. And so all the wires were beginning to produce thermal energy out of, or thermal power out of the battery's power. But that wire in particular produced a lot of thermal power and got red hot. So the point of all this is, the public service announcement part of this is suppose there were no protections on the electrical wiring in your house. It just could deliver as much electric power as you like, no limits. And instead of plugging in, a toaster or a lamp or something like that, you just plugged in a paper clip. You would not be the first person to do this. I never did this, but there are plenty of people who have done stuff like that. This is the little kid problem. Oh, that! Okay, so you basically create a short circuit by doing that. And another way to make a short circuit is you have your lamp on an extension cord across the middle of the floor, where there's a rocking chair, and people have been rocking back and forth over that lamp cord for the last week and a half. And eventually they've just crushed all the rubber and plastic in it, and its two wires touch each other. You know it's got two wires. Why do you know it's got two wires? Because it's the lamp's job is to get power from the power company, not charge from it. So the charge has to arrive through one wire, drop off power, and go back to the power company through a second wire. So this is all the cords that you encounter for plug-in devices. They all have at least two wires in them. And those two wires are meant not to touch each other. One is the delivery wire, one is the return wire. And if you crush it with the rocking chair or pinch it, or you've got pet bunnies are the most notorious for chewing on wires. Chew it until it instead of being two separate wires, it's one connected wire. It's a short circuit. So now instead of the current going out to the lamp, lighting the lamp, and then returning to the power company, the current goes out halfway through the cord, jumps over to the return wire, and goes back to the power company with nobody in between. Nothing to consume the power, so the cord starts getting hot. So when they tell you, and I guess they enforce this stuff around grounds surely, being careful with extension cords and all that kind of stuff. They're concerned in large part about, well, about two things. One is short circuits. You don't want, I mean, that's really a problem. Typically, the electrical system is protected against short circuits. If you have a short circuit in a typical, the cord for a lamp, for example, it will, the protection system will turn off electricity to that outlet. The circuit breaker will pop. It used to be a fuse would burn out, and then you had to go buy new fuses. Circuit breakers are a nice innovation of, I don't know, 50 years ago or something like that. Prior to that, you really had fuses, and that meant when they popped because of excessive current flowing through them, due often to a short circuit, you had to replace them. They were disposable. Circuit breakers are resettable for the most part. All right, so those are short circuits. Even if you don't have a short circuit, but you're simply consuming a lot of electric power through the wires, as I mentioned before, the wires don't carry electric current for free. You have to push the current through them. And it turns out that the amount of current that goes through a wire depends on the voltage drop across it. The more voltage drop you put on a wire, not surprisingly, the more current flows through it. Why? Because you're pushing harder on all the charge. Bigger voltage drop means bigger electric field. So you push harder, more current flows. The characteristic of the wire itself matters. As we can see, the light bulb filament is a terrible conductor of electricity. Therefore, you have to push especially hard. To get even a modest current flowing through it, you have to have a big voltage drop across it to push. What I'm heading towards is one more. I'm trying to pick off the pieces I want to tell you about, make sure I've told you. This observation that the current that flows through a wire, or anything like a wire, depends on the characteristics of the wire. That is, how difficult it makes for current to flow. What's called its resistance. The current that flows depends on the resistance of the wire, and it also depends on the voltage drop across the wire, which is in a sense how hard you're pushing on the wire. That relationship, and I'm realizing as I see it here, it is a little bit confusing cause and effect. This is a little bit of one of these relationships that I should rearrange. What's really going on is the current that flows through a wire is proportional to the voltage drop across it. The voltage drop is the cause. That pushes the current along. The more voltage drop you have, the more current will flow because you're pushing harder. And the resistance to current flow is literally the resistance of the wire. So I should really divide both sides by resistance. I should really have this written as voltage drop divided by resistance equals current. The cause then would all be on the left and the effect would be on the right. Current is what is the result. This relationship is always written this way, though, out of long history. It's called Ohm's Law. It dates back to actually a high school teacher. Ohm was a high school teacher who observed this behavior and ultimately had it named after him. And it's remarkably accurate for a huge variety of things carrying electric current. The amount of current that flows through those things is almost exactly proportional to the voltage drop. In other words, how hard you push. And it's almost exactly inversely proportional to the resistance. That is, how much that material fights the flow of current. Okay? In this situation, what was the point of doing all this? To come over here to this situation with the light bulb. I've arranged it with a short circuit present right now, that the highest resistance in now short-circuited circuit is that piece of wire there that's glowing red hot now. So to get the current flowing through these wires is pretty easy. They only need a little voltage drop to get the current going. But to get the current going through that bad wire there, that chunk that's not so good, you need a big voltage drop. You have to push harder through it. So most of the voltage drop available, the battery gives us a voltage rise to work with, And where does that voltage rise sort of degrade by way of voltage drops? Mostly in that wire. So that's the wire that's it's got the biggest push to make current go through it. And because it's got a big voltage drop and a lot of current flowing through it, remember, the power delivered is the voltage drop times the current. Well, that's a big number for that guy. It's getting about 1,000 watts of thermal power, and it's getting nice and toasty. All right? I will stop this before we burn up too much stuff. All right. So I've given you an introduction to Ohm's Law. Ohm's Law just shows up as useful. It's useful in a lot of electronic devices as well. It's just one of these observations of nature that so many things behave like that. You can use it. You can work with that relationship between voltage drop and current. Okay? Any questions at this point? I have two more things to talk about, and I don't need anything here at the moment. Let me come over, zoom in. Preset 2, does this work? Oh, close enough. Close. I'm going to shift this over into view. So I've got 3 batteries, 3 familiar D cells. Amazon's taking over the world here. So 3 D cells, all arranged so that their positive terminal is to the right at present. You can see the little plus signs on them. And that means that if charge arrives here at 0 volts, this one will pump charge until create a voltage rise of 1.5 volts. These truly are alkaline batteries. And they tell you that, alkaline, right there. Okay, so anyway, 1.5 volts, 3 volts, 4.5 volts. It's a 3-cell battery chain. And if I complete the circuit, the light bulb starts glowing. And what's happening is the charge arrives here at 0 volts. It's pumped up to a 1.5 volts, to 3, to 4.5. It goes through the wire with a small voltage drop to keep current going through the wire. So maybe it's 4.4 volts by the time it gets here, having lost a little bit in the wire. It goes through the light bulb filament, which gets red hot. It's not a good conductor of electricity. It has a large resistance, so you have to push hard to get current to go through it. And so you have a big voltage drop across it. It's carrying a fair amount of current at a big voltage drop. That's a lot of power being delivered. And the light bulb gets nice and toasty. And then the current continues through the last wire back to where it started with a little push in the wire. The wire is a good conductor of electricity, and so it doesn't charge very much. It doesn't require much of a voltage drop to keep going. So far, so good? What if I reverse one of the batteries? So I'm going to take this battery out and put it in backwards. I'm not sure you can see. It's glowing a little bit. So this is actually a complicated story, what's going on here. The charge arrives here at 0 volts, pumped up to 1.5 volts, pumped up to 3 volts, and then it goes through the third battery backwards. It actually does continue on. This battery would like to have current go the other way, but these two guys are ganging up on it, and they win. They push current through this battery backwards, and it runs the chemistry backwards, and we are actually recharging that battery. Its whole electrochemical process is being undone, and it's not good at receiving that energy back. It won't recharge well because it's not designed to recharge well, but it is recharging a little bit. And so the charge at this point has gotten to 3 volts. Out here, it's back down to 1.5 volts. It lost 1.5 volts. There's a 1.5 volt voltage drop in that battery because it's become a consumer of electric power, not a provider of electric power. So we've only got 1.5 volts here. That's not enough to push a lot of current through the light bulb filament, and the light bulb glows dimly. Not enough voltage drop. Fiona? If we only had 2 batteries, would they completely cancel each other out? Yes, exactly. If I do that here, like this, nothing. This is now a 2-battery battery. This one that way, that one's that way. They're doing nothing. So the fact that I've got 3, I had to arrange it to have 3. Otherwise, it's a battle over, paralyzed battle. Now I've got 3. 2 of them can gang up on the other. If I flip the middle battery, you see this guy glowing a little bit. If I flip the middle battery, it's still glowing weakly, almost identical, but the current has reversed. We now have these two guys ganging up on the third one. So the current, it starts at 0 volts here, 1.5, 3, back down to 1.5, and it's running backwards. We actually reversed the current in the circuit. So that this guy, you can flip it back, nothing will happen. If I flip this guy, now we're back to full power. All right? So a point of showing you this is that if you have lots of batteries, you can work your way up higher and higher in voltage. Lecture demo accumulates a lot of these 9-volt batteries. I don't know if you ever sort of saw 9-volt batteries. Have you ever noticed that you can attach 2 9-volt batteries together? I do that once in a while. I had one sitting here. Yeah, I don't want it. The little pieces you put, and so there have been times when they put together strings like 100 of them, and you actually get 900 volts between the entrance and the exit. You have to start getting careful with those, because the charge keeps going to higher and higher voltages. It gets pumped by one battery after the next. Usually one or the other of them in this chain goes bad, and then it ruins the whole effect. But the basic idea is correct. You can get lightning bolts if you put 1 million of them together. Yeah? How is the charge moving from one to the next in this circuit? It's moving through wires. There are wires connected. So these are little mounts for batteries. They're very simple clip mounts for batteries. So there is a contact on this side allowing charge from this wire to enter the battery at its low voltage end. There's another clip over here to let the charge out at the high voltage end, and so on. Can you see that piece of wire there? And there's a piece there too. All right? Thanks. Yeah, and getting the connections are of course important. Any failure in the connection, the circuit's broken now. The whole process fails. And so that's a familiar thing with flashlights and stuff, that when you turn on, there's nothing, and you sort of shake around trying to get the connection to make. Even in the modern flashlights, that often enough happens. It happens with me with my laser pointer. The laser pointer's got a circuit in it too, and nothing. Oh, there it went. This guy drives me nuts. About half the time, the circuit's imperfect. Now I've ruined it again. Come on, guy. Anyway, circuits are hard to keep intact in some of these overly simple devices. Any questions then about multi-cell circuits and recharging cells? I mean, your cell phones, I'm going to just say 2 more cents about that. Your cell phone, I went on this a little bit last time. It's amazing that your cell phones require sort of no user intervention to do the charging. It used to be you had to take the batteries out of whatever you were, rechargeable batteries, yeah, they were sort of rechargeable, but you had to remove them from the device that was using the power and put them in a device that charges them, and you hope that the batteries took the charge well, and they didn't always do that for interesting reasons, and then you had to put it back in. I mean, that's all gone. And the batteries, you just plug it into your computer, you just set it on the charging widget, it charges. To give you an idea of the problems with old rechargeable batteries, the earlier generations, they had behavior known as memory. It was a jargon name for remember memory of what? The memory was that if you use the battery, suppose you charged it fully, it was great, it was brand new even, and you used it 10% of its capacity. So you used 10% of its stored chemical potential energy doing whatever it was supposed to be doing, and then you charged it again. It would remember that 10%, it's got from full power, the total energy to zero energy. It would remember that you pulled it down to 90% at one point, and it would develop a little bit of a chemical problem at that point. So as you're now using the battery, when you've used 10% and are right back where that last time you charged it, right at that point, it would suddenly have a bad spot where it just couldn't deliver very much power for a while. And you had to work your way through that bad spot to get back into the good territory where you got good electric power out of it. And as time would go on, you accumulate more and more of these bad spots, and you're actually, the structure of the battery would be imperfect at that point because you didn't discharge it and then recharge it. So you actually had to deliberately discharge the batteries all the way down to almost flat broke and then recharge them to try to erase this memory effect. It was, it's just terrible. As a kid, I thought rechargeable batteries were just so wonderful, and then I would talk to grown-ups that actually had to live by them and use them, like a photographer friend of ours who just thought they were just the most miserable thing you ever imagined. Drove him nuts. And this is all gone. The batteries that you're working with now have essentially no memory. You can charge them now. You can use 1% of their power and recharge them. You can use 100% of it, recharge them. Who cares? Nothing, and they work for a year or two or three, and almost no decay in their behavior. It's pretty amazing. Okay, enough of my harangues on that. I had one more thing to show you, and that is what are known as series and parallel circuits. And I've talked a little bit about these ideas. If you arrange, so this is a circuit. I can get this guy out of the way so it's not cluttering our view. This is a circuit where instead of a battery, I got the electric power company here, but we'll see that that's essentially a battery living over here. And this is what's known as the schematic symbol for, it's the symbol for a battery by convention in a drawing of an electric circuit. So all the objects that one can imagine that you put into an electric circuit have a symbol associated with them if you want to draw the circuit on a sheet of paper. And that's the symbol for a battery. Anyhow, it's not so important. We can create a circuit where there's the battery, the source of electric power, even if it's not a physical battery. And these right now I've got arranged, so these are just funny looking wires. They're just wires going over here to 2 light bulbs. And if I turn this on, the 2 light bulbs are the consumer end of the circuit. We've got a battery, wires, and 2 light bulbs. And the 2 light bulbs right now are arranged in what's called parallel circuit. They're in a parallel circuit. What does that mean? It means that as current is flowing along, and this is officially the positive side of the battery for whatever, as though that matters. The current is coming along like this, and it arrives at this point on these 2 drawn wires here, and it's faced by a choice. The current can go through this light bulb or that light bulb. And so the current divides. In this case, it actually divides pretty evenly. And about half the current that was coming from the battery goes through this light bulb, and the other half goes through this light bulb. And then the current leaves the light bulbs, having given up most of its energy, or most of its power, and it reconnects, joins up again, and continues back to the battery power company to pick up more energy. I'm going to turn this off because it's dazzling me. But the point is that when you have two electrical devices in parallel, they share the current, and they both experience the same voltage drop, or in the case of batteries in parallel, the same voltage rise. So the voltage arriving here was, if I were using the car battery, that would be plus 12 volts here. The current would divide and go through the 2 light bulbs, and then it would rejoin at 0 volts. So the point is, 2 light bulbs in parallel share the current but experience the same drop in voltage. So, you okay with that? What's the alternative? The alternative is this. Let me undo this funny wire and move one of these light bulbs, come back here, to there. Now the circuit's different. Instead of having the current leave the battery and go through one or the other of the light bulbs, the current goes first through this light bulb. These guys are doing nothing here. Through this light bulb, and then through that light bulb. They are now in what's known as series. So in a series arrangement of 2 electrical devices, the current goes through both of them, one after the next. And the voltage drop across the pair is, they both have the same current flowing through them, but they have to share the voltage drop. Each one takes a little bit of some fraction of the power going through being carried along with the current, and they now glow dimly. And the reason they're glowing dimly is because we have only a certain amount of voltage difference between entry and exit. If it were the car battery, it would be 12 volts. So they can't each of them take 12 volts of voltage drop, because whatever voltage drop this one takes is not available to that one. They have to share the voltage drop. So if that's 12 volts grand total, this one might take 6 volts, and this one might take 6 volts, and 6 and 6 is 12. They get, overall, they're taking the entire available voltage drop, but they're taking it, they're slicing it up, slicing the pie. Yeah? How does the first light bulb know to share? That's a good question. It's a negotiation, actually. So if the first light bulb tries to take too large a voltage drop, then a large current goes through it, because a large voltage drop means there's a big push. So the current flow through it is large. A lot of current shows up here at this light bulb then, but there's not much voltage drop available anymore, because this current's showing up, and there's almost no voltage drop left for this guy. So with a small voltage drop, that large current won't flow through it. So the current backs up here. It tries and realizes, oh my God, we can't get through there. It's a bottleneck. So the current begins to accumulate here, and the voltage here begins to increase as charge builds up. And this guy starts losing its voltage drop. So they try briefly negotiate, what do we do? And they've now negotiated a settlement, which is each of them takes, because they're essentially identical light bulbs, each takes half the voltage drop. Is that okay? There are a lot of cases, it's an interesting question, because some of the stuff in a normal class, normal physics class, it's just, the answer is just because. Like, no one would ever question any of this stuff. But these negotiations happen all the time. I told you the negotiation of when you put the ball on the table, or the wagon on the table, and it negotiates with the table for just how hard to push. These are all parts of life that are always swept under the rug in normal classes. If I make these two light bulbs not share, have different electrical resistances, they'll share unevenly now. This guy's got the biggest of electrical resistances. It's a low wattage bulb, which means it doesn't carry very much electric current, even when exposed to full electric power from the power company. So it gets pretty hot even when a small current's going through it. This guy is a higher wattage bulb. It wants more current to work. So what's happened is they negotiated a weird settlement. They're certainly carrying the same amount of current. They have to. Current, like charge, is a conserved quantity. Current, because it comes from charge, is conserved. So the current that goes through here has to go first through this light bulb and then through that light bulb. But because this one's got a high electrical resistance, it being a low wattage bulb, it gets a big voltage drop. It gets almost the whole thing. This poor guy carries the current too easily. It doesn't demand a big voltage drop. So there's a little voltage drop on this one, big voltage drop on this one. This one's pretty much happy. It's almost, it thinks everything's great. I hope that's sort of followable. Is that okay? I think I've said everything I wanted to say about electrical circuits associated with flashlights. Any questions about flashlights, electrical circuits? It's not the end of circuits for us, but it's the simple piece of them. The next time we encounter circuits, which will be very soon again, it'll be really electric company circuits. And electric company circuits have an added level of complexity because they carry what's called alternating current for reasons that they're partly historic and partly still necessary, but things are evolving. Anyway, they've got a level of complexity on top of them that's sort of a nuisance, but we'll have to deal with it. So I'll bring this back up. I'm going to seemingly take a huge leap into something unrelated. And something unrelated is household magnets. And what's the story here? Of course, the household magnets. Why would I go off in magnets? I was just talking about electric stuff and the movement of electric charges through wires and how energy can move from one place to the other, or if it keeps moving at a steady pace, now I start trying to talk about it as power. Why would I suddenly leave the world of electricity and all that stuff and just jump right into magnets? What, they're off the wall. I mean, and so the background behind this is, for a little while, magnets are going to seem like their own little territory. Another interesting collection of phenomena in the world. And then we're going to discover, electricity and magnetism they're not even first cousins, they're like siblings. They are so closely related, and they have all kinds of overlap. So I can't leave out magnets. I can't go too far along with electricity before I have to drag magnets kicking and screaming into the picture. So here they are. And they'll start off as seemingly a separate world. And as we'll see, there are some startling similarities between the world of electric charge and the world of magnetic pole. And it's not a coincidence. They are very, very closely related. Okay, so the first observation, I sure hope you still play with magnets to some extent. You stick stuff on the refrigerator with magnets, and maybe the current crop of magnets that you can just purchase for not very much money are amazingly strong compared to what they were 50 years ago. Here's another case where technology advanced a lot, and just any old, it used to be that strong magnets, if they existed at all, were extremely expensive. Now, they're a dime a dozen, and you can get them so strong they easily pinch your fingers and cause trouble. Okay, so hopefully you play with magnets. And so the question that I'll start off with is, suppose you have a bar magnet, like this bar magnet, and it's got what as we'll see has been given the name by convention a North Pole and a South Pole. And this is for geographic reasons having to do with magnetic navigation and compasses. Anyway, it's got a North Pole and a South Pole. And the question is, if we break this guy across the middle, like this, will you end up with, so you end up with two ends. In fact, I can do it. Oh, broken. Oh, there we go, okay? Yeah, right. Will these two broken ends attract one another, repel one another, or neither? You okay with the question? So you know the opposites attract and all that kind of stuff. How many think that they'll attract one another? How many think that they'll repel one another? How many think neither? Okay, there's a stronger vote for attract than repel. Yeah, they attract one another. And the explanations you could think for that are, well, maybe when I broke it, okay, that this is now a pure North Pole and that's a pure South Pole and opposites attract, and so of course they attract. But it's actually more subtle than that. And to give you an idea of why it's more subtle, opposites do indeed attract. I'm going to start playing with these guys. So these are on swivel, so I can look around. And assuming that all the red marked magnetic ends are what are called North Poles and the whites are South Poles, then this North Pole and that North Pole should repel, and they do. Same over here, okay? And this South Pole over here should attract, it should repel a South Pole. Does it? Yep, sure enough. Okay, oops, come back here. It should attract the North Pole, and it does. Okay? If I break this, if this is pure North Pole, then both ends of this guy should attract the South Pole. Let's try the original tip. Sure enough, it attracts the South Pole. But let's try the broken end, this guy. And it attracts the North Pole. Can you see that? That isn't North Pole anymore. It's South Pole. So what happened when I broke this guy? This is really North Pole up here. This is really South Pole. When I snap it, the two broken ends develop their own poles. The broken end of the North Pole, of what the former North Pole, becomes a South Pole. And the broken end of the former South Pole becomes the North Pole. Where this is going is, this magnet, when it started, it does indeed have magnetic poles on it. And magnetic poles are very much like electric charges. But unlike, if this were an electric, a bar electric, it's not even a magnet. This is called a bar magnet. If this were a bar electric with a positive charge and negative charge, if I snapped it, I'd have positive charge here, and I'd have negative charge there. We did that, some of the examples, the pot touching the pipe example did that, okay? In this case, when I snapped it, I didn't end up with any North Pole and any South Pole. I ended up with pretty much the same situation I started with, but just on a smaller scale. What is that situation? The situation is this, that there is in nature a conserved quantity, which could be called magnetic pole. It's like another conserved quantity. Electric charge is conserved, magnetic pole is conserved. And this magnet does indeed have an end that has a net North Pole on it and an end that has a net South Pole on it. They're not called positive and negative just because we use those words already for charge. So North Pole is kind of the magnetic equivalent of positive, and South Pole is the magnetic equivalent of negative, just to give them different names. So this has some North Pole up here, it has some South Pole up here. The net pole on this object is exactly 0. It's magnetically neutral. And when I break it, the two halves are magnetically neutral. Everything's magnetically neutral overall. What that means is that no one has ever convincingly found a free North Pole, a North Pole all by itself, or a South Pole all by itself. They always come in equal and opposite pairs. And we've seen equal and opposite pairs in charge. That showed up when you polarize something. If you hold a electrically charged candy wrapper near a window, the window develops an electric polarization. It doesn't have a net charge, but it has a positive end and a south end, a positive end and a negative end, okay? But that candy wrapper you started with had a net negative charge in my story. That doesn't happen with magnetism. Magnetism is weird, it's different. There are no free poles. So you can't get a candy wrapper with a net North Pole on it. They don't exist, as far as we know. People have been looking for them for a long time, and there have been a few seemingly observations of them. But as far as we know, they're not around. They would be called magnetic monopoles if they were found, and they are just not observed. So the magnetism that we see is a little bit more subtle than the electrism we see, because we don't have free magnetic poles. You got to work with pairs and things related to it. All right, well, we'll return to this on Monday and continue along.